So in this part of the ourBotManager, going to check on my checklist. You see here, so I've done the two ROS courses, ROS 1 and ROS 2. I've got links down below to the Udemy courses I used. They seem pretty good. And I've done the hands-on part of learning more about motors and how they work. And so now I'm going to look at putting together the final version of the base motor controller, which is going to control the two motors in the robot base to keep them in sync, moving the same distance. And also going to put together a serial interface to that so that I can control the base motor controller from a ROS node. And I think that's mostly most of the preparation work. I'm probably not going to do the battery checklist items here yet. And I've got the Raspberry Pi working as part of the network tests I did on the last video. So I may run through that again, how I set it up to get Ubuntu and ROS 2 on it. And I think that's going to be most of the work I need to do until I get an actual robot base to start playing around with. Okay, getting an idea of what I want to do with my robot architecture now. So I'm going to use ROS 2 for most of the operating system. I'm going to create, and this is what I'm going to talk about in this video, is the base interface. So managing the connection to the base controller, so the thing that actually moves around the robot's motors and wheels and things. For the base interface, I'm going to have it receive fairly standard ROS 2 messages, so the twist message for telling it how fast to move and what direction to turn, and then return odometer meterings and pose messages. Most of the logic for this is going to be on the Pico microcontroller, managing the actual motors. So to allow them to talk to each other, I'm going to set up a simple serial interface, just a custom serial interface to talk between this base interface that runs as a ROS 2 node and the actual base controller, which is that Pico microcontroller. Okay, here's the idea behind the motor controller. So it's controlling two motors, one on each side of the robot. As it goes along, the encoders for each monitoring cycle, which is a tenth of a second, will output a certain number of ticks. If one side slows down, hits an obstacle, or runs into something that slows down the wheels, then the number of ticks from one side in that monitoring cycle is going to be different from the other side. So what it'll do is, if it sees that different, it'll slow down the other side's wheels to get them aligned again, going the same speed. And then as soon as they got through the obstacle, it'll try and speed them up to the full speed again. Now that may not totally correct the number of total ticks from the encoders for the total distance. So if there's still a discrepancy there, there's also another routine that looks at the overall distance or ticks from the encoders, and will also apply a correction. It'll just be a small percentage of the overall correction over a number of monitoring cycles until it corrects the number of ticks, so it stays in balance. So I have my test bench set up with two motors, and this code is testing out keeping them in sync. So I'll have a look at the code in a sec, but at the moment you see both motors are running full speed, and if one goes a little slow or gets slowed down, then the other one gets its speed adjusted to compensate. So here's the same thing. I'm going to run it, but I'm actually going to grab hold of the motors in this case to slow them down manually, and you should see the motors readjust to actually end up going the same speed and going the same distance. And we can see that in both the OLED display here and in the reporting out the Python script, showing the motors have done almost the same distance. And finally, this is one more run where I'm running at a slower speed, so 50% duty cycle. Just to test the same thing, that if I impede one motor, that they work it out and readjust themselves, so they've gone approximately the same distance at the end. So here's my hack together code for testing out dual motor controller. So main thing is in the main routine, it'll set a status timer every 10 times every second. It's going to fire off the status timer to check the status of the encoders on the motor, see if it needs to adjust the speed. Base speed is the speed I want to go at. And again, once this is connected up to a ROS2 node, that's the main information being passed to the motor controller, is what speed do you want to go. So let's have a look here. So update status is the thing that gets fired off once the motor's going 10 times a second, and it's going to report out to the OLED on the speed of each motor over that tenth of a second, and we'll call this adjust RS speed. So this is the thing that's changing the speeds of the motors to keep them in sync. So if the encoders have got a value other than 0, so really that first cycle that'll all be 0, so after that they should all have a value in there. Then it works out the speed difference for that monitoring cycle, and then also works out the distance difference over the whole distance that the motors have traveled. So this is the distance they've traveled over a monitoring cycle, this is the total distance they've traveled. And then down here, if one motor controller has traveled further, has more encoder ticks for that monitoring period, then it adjusts the speed for the opposite side motor downward, and same thing over here. And then it also looks at the overall distance travel. If there's a difference in distance, then it also adjusts the speed down on the opposite motor to get them on sync. There's this DF factor, which means that it doesn't apply the speed correction in one go, doesn't try and get it exactly right in one go. That seemed to cause some weird oscillations with the motor, so I just do it over a number of monitoring periods until the total distance is in sync, and then it sets the new speeds based on whatever it set the speed to after the compensation. Now I'm going to change this code around. This seems to be working, but I'm going to bundle it all into one class. I was going to clean up this L298 class now, so instead of calling it that, I'm going to call it something a little more generic, because I found it's not just L298s that this class can control. Pull all these things like the settings for the pulse width modulation, pins and things up to a higher level class. So there's just one class that I just pass the speed to it. It'll do automatically under the covers synchronize the speed of the motors for me. So let me go through, and then I'll show you the resulting code after that. Okay, I got to the point where I need a proper repository for my code. Sort of been playing around in a test repository, but now I'm going to move things into a GitHub repository. One problem I'm having is it's actually targeting 3 platforms. So ourBotManager, there's going to be Angular and Firebase code, which targets one platform. It's going to be microcontroller code that's going to target microcontrollers, and then there's going to be the ROS code for nodes and packages and things that is going to target Ubuntu in the ROS environment. I can't think of an easy way to put them all into one repository and have them get deployed to the different platforms. So at the moment I'm going to set up 3 repositories in GitHub: ourBotManager, ourBotManager underscore microcontroller, and ourBotManager underscore ROS. I think eventually I might be able to combine the ROS and the microcontroller repositories. They should be able to exist together because of the way microcontroller code gets deployed. But I think this one's always going to be a separate repository. And for the rest of this video, I'll work on the base motor controller. That'll be my new name for it. Just bring in the code that is working well and that I really need for my my base controller, and hopefully I'll get the serial interface worked out in this video as well. Otherwise maybe the start of the next video I'll have a look at what I do to get the serial interface working between microcontroller code and ROS node. So this is the updated code after I moved it into its real repository. So like I said, I created an ourBotManager underscore microcontroller repository, and in there I've put just 3 Python scripts. So hbridge is the thing that controls the hbridge motor controller. So this little device here, or is the class that interfaces to it. And then base motor controller is my new class that represents the motor controller, does all the synchronization of motor speeds and does turns and runs now. And just to show an example of it running and why it's a lot simpler, so up in the main program for testing it, so now I just fire up the class base motor controller, make an instance of it called BMC, and I pass all the pins that are being used. So the pins for the pulse width modulation for the left and right motor, pins for control of the motor, forward, reverse, stop and things, and then the pin that's being used for the data being, or the text coming back from the encoders on the motor. So easy to set up, and then I can just run these commands. So there's an example of running or moving forward at a velocity of 90 for 3 seconds, and then stopping, and then turning at a velocity of minus 40 for 3 seconds. So let's try that out and see if it works. So that's running forward, both motors going the same direction, we're stopping, and then we're going to do a turn. So you see the motors are going at a different speed and reverse direction, so it performs a turn on the robot. So let's have a little look at the code, and then I'll have a look at the serial interface. So this is the base motor controller class, so kind of evolved from that earlier code in this video, where I've cleaned it up a bit, turned it into a class, and also added both run and turn capabilities. The other thing I did is, rather than having to designate whether a velocity is a forward velocity or a reverse velocity, it just uses whether the speed being passed is positive or negative to decide whether it's going forward or going in the other direction for both running and turning. So when you start up the class, to initialize it, it takes all the pin assignments that have been used on the Pi Pico. It resets all the variables, and there we see the 2 main functions that are exposed. So the run, so you just pass it a speed or a velocity, and it will run and keep running at that speed or velocity until it's told to stop. And then we're using that same adjust left-right motor speed to keep the 2 motors in sync, so that one doesn't go faster than the other, or if it hits something, doesn't impact the direction, or for the turn, it may impact the robot forward. By keeping them in sync, it'll just essentially just do a straight run or a straight turn. And I think that's pretty much, otherwise just the code that we had before. I also added in garbage collection. I tried to put it in a places where it's not going to impact the ticking if it goes off and does a garbage collection while it's counting encoder ticks, that sort of thing. So it seems to be okay. I still get accurate results and motor synchronization even with garbage collection going. And looking at the amount of free memory as this thing runs, it really needed the garbage collection. So now let's have a look at what I'm going to do for a serial interface for this, for actually setting the run and turn commands to the base motor controller. So this is the plan for the serial interface from the Raspberry Pi 4 board that's going to be my ROS2 platform. It's going to connect from the USB via USB cable to a FT232 device, which is a USB to UART device. And then that will connect by UART or serial into the Raspberry Pi Pico, which is running the base motor controller. So I'll use custom serial commands to do the equivalent of a twist, tell it to run or turn at a certain velocity. And then I'll have this board returning, again through the serial interface, distance moved for the complete base, so kind of odometer readings going back, and what direction the base is pointing using a kind of a pose command. But they'll be all custom. It won't be the ROS2 versions, but by the time it gets to the ROS2 platform, then the node will convert it to the correct format for use in ROS2. I did a little testing of this, so I found when I connected up an FT232 device via USB to my Ubuntu on Raspberry Pi 4, I could do a LS USB, and it recognized that there was a FT232 there. And also when I look back at the recent messages, I did a group for USB, and I can see here where the device has been recognized and it's actually been assigned. You can see here to dev TTY USB 0. So that should be the way I can write the Python program on the Raspberry Pi 4 to talk serial to the Raspberry Pi Pico motor controller. I went this route. There are some UART outputs on the Raspberry Pi board here, but I see that people have had difficulty using those, both because they're in use for other things for the Raspberry Pi by default, and people had trouble getting Ubuntu to talk nicely to the built-in UART. So I think this is going to be easier, and it's probably going to be easier for cabling too, just to run a thin USB cable out to the motor controller rather than a twisted pair or something of UART cables down here. So I've got the base motor controller being able to be controlled through serial now. I'll go into the code for that after this demonstration, but let's just have a look at it working. So I have Termite running, which is just a simple serial terminal. It's connected up to the base motor controller through an FT232, and using this I can send commands to the base motor controller. So let's try some simple ones. So I'll go through what the commands I'll set up are, but for example I've got this one which is run with velocity of plus 20, and you see the motors are moving there. I can do a SP for stop, and I can also control the distance. So this one here is a turner distance, move in velocity of minus 50, so anti-clockwise, and go for a 20 encoder pulses. So let's try that one out. So we saw the turn there. We see down here it's keeping track of it. It went a bit further because it basically just stops once it exceeds the distance target. So it went 230 pulses versus 200. So I have to wait until I get it in a real robot whether I do more tuning on this. That may be close enough for what I want to do with it anyway. And just another example of a run for a distance. So this one is run distance at 50, speed of 50 or velocity of 50 for 500 encoder pulses. So you see here runs over by about 8 or 9 pulses. So let's have a look at the code. Just before we have a look at the serial code I added, just a note on the serial commands. So these are the commands coming from the ROS node I still need to write going to the base motor controller. So they all end with a carriage return to indicate the end of the command. So the commands are SP for stop, just stops the motors moving. QT for quitting the base motor controller process. Normally it runs in the background on the controller, so this shuts the whole thing down, but just be aware you'll no longer be able to communicate via the serial interface. Next one is RB for rebooting the base motor controller, and that should get the whole thing running again as a fresh instance on the Pico controller. And then the ones for actually moving things. So RV is run at a velocity, and then I specify a positive or negative sign, and then the velocity to move at. So the velocity can be anywhere between 1 and 100. TV, similar sort of thing, but for turning the motors or the bot at a certain velocity, and the sign in this case will indicate whether it's clockwise or anti-clockwise for the turn direction. And then some smarter controls, so RD for run distance, so it'll run a distance at a certain velocity, just like the RV one up here, but it'll only do it for a certain distance, which is the average of the two motors distance seen. And then same thing for turning, but turning for a distance at a certain velocity for a certain distance. So this is how you can get an absolute turn, so say 90 degrees. Just note on these units or measures, so they're all in ticks at the moment and aren't specific to the actual base. So what I expect to do is up in the ROS node to do the conversion for, depending on the distance between the wheels and the size of the wheels and things on the actual robot to send the right number of distance ticks to go, or the speed to go to get certain meters per second. But I only do that once I got the robot put together and can put some tuning parameters, but those will go into the node rather than into the lower level base motor controller. So let's have a look at the code. So let's have a look at the additions and changes I made to the code. Mainly to do two things. One, to keep reading serial data coming in, and the second to manage the new commands like moving a certain distance. So at the beginning of the code, you see here I now bring in the UART class, set up the UART or the serial interface, and also have a couple of new motor control variables. The main one's the base target distance, which would be the distance we want to move if it's greater than 0, so the target distance to move. Let's have a look down here. Okay, so there's some new commands in here. So as well as just run, we've got now run distance, which takes a speed and a distance, and it sets up that base target distance to whatever distance is requested, and then runs the run command. Same thing for turn. We've got a turn distance command available now. So the way we get the serial interface listened to is now in the monitor status. So this is the callback that gets called every 1/10 of a second. This runs all the time. So if the motor mode is not L for listen, means it's being asked to do a run or a turn, then it does the adjust speed like we saw before, and then does a UART listen, or if it's just a listen only mode, so the motors are stopped but we just want to listen for commands, then it'll just drop through and do the UART listen routine. So this is the bit that listens for new serial commands coming in. So let's go down and have a look at that one. So this is the UART listen. So I had to spend some time with the UART to work out how to get it to run where it wasn't blocking. So basically it goes out and does a non-blocking read of one character, or if there's any characters available in the UART. Normally it'll just append it to the UART data for this class. So it just adds the character to that until it sees a carriage return character. That indicates that we need to process that command. So it calls process data, and then it'll clear up the command ready for the next command coming in. So the process data, so this is where it's got the complete command in theory in UART data, and then depending on the length of that command, it's going to do some validation. So if it's too long, then it's going to be one of these three commands: stop, reboot, or quit. If it's 6 long, then it's going to be some sort of velocity command, either run velocity or turn velocity. And it's also got a try catch in here, or try except, to check whether the velocity actually converts to a valid integer or not. And if it's 11 characters long, then it's going to be a run distance or a turn distance command. One note here: if these conditions aren't met, then it's basically going to set command to blank, which indicates there wasn't any command or any valid command that came in. Then finally, part of this code is if a valid command is there, so the length of the command is greater than 0, then I'll execute the actual command based on the serial command coming in. So if it's quit, tells the base motor controller to stop and then quit. If it's just stop, it'll just do a stop. If it's an RV, then it'll do a run with that, whatever the velocity is. If it's a TV, it'll do a turn with that velocity. And same thing, if it's a run with distance, then it's going to call the run distance routine with whatever the velocity and distance is that was passed through the serial command. Same thing for turn distance. That seems to work. I was worried that my timing will get out of sync and that the motor sync and all the interrupts that are going on would interfere with each other, but it seems to work okay for this. And then if I see there's any problems, my plan is I'll swap from a Pico up to probably an ESP32 that's got a higher clock speed, probably get more done in the same amount of time. So if I run into problems with the interrupts sitting on top of each other or getting into race conditions, then that's the plan. The other route I could have gone with the serial is to use the poll command to make sure it's not blocking. Also to use some threading. So again, if I run into problems with this not being reliable, that there's too much going on to run it synchronously, then I'll start using some of those things to get a more synchronous code going. But I'm not going down that route unless I really have to. The other note, I made a change, so I can either show the debug commands or the print commands on what the statuses are based on when I start up the base motor controller. If I call start with true, then it's going to show the debug commands like we saw in the demo. Or else normally in production I'd set it to false, so it doesn't do any of the print commands as well, which should reduce some of the workload. So that's it. Next video I'll probably be looking at the actual node, ROS node, to interface with this, and that's going to take more like a standard ROS twist command, and then send it down to the base motor controller, but converting the twist parameters into what the base motor controller wants to see in terms of encoder pulses. That should then work with something like a keyboard control in ROS as well, to start having things respond to just a keypad for moving the robot around.